Good afternoon, sir.
Hi, good afternoon. Yeah, good afternoon, every one of you. So until the last class, we were seeing the humidification, unit 2. So far we have covered the contents, humidification and definition of humidity and various forms of humidity, enthalpy, humid volume, humid heat, wet bulb and dry bulb temperature definitions we have covered. So humidity chart and use of humidity chart we have covered. So vapor pressure curves. Today we are going to see this vapor pressure curves. So what is this vapor pressure curves? For example, it is nothing but a graphical representation of temperature versus pressure. Okay, at which the liquid phases, where phases will be existed. So for example, let us say if you want to take a boiling point of water, everybody knows the boiling point of water is 100 degrees centigrades. So how we are saying that one? So 100 at 100 degrees centigrades, its pressure will be equal to 760 mmHg. So at 1 atma only, that boiling point is equal to 100 is valid. Okay, if you change the pressure, okay, decrease the pressure further, your boiling point will be decreased. Okay, depending on this line. So these lines are called the vapor pressure curves. Okay, depending on the pressure and temperature, how these curves will be lying. For example, this is a water curve. This is a ethyl alcohol curve. So whose normal boiling point is 78.4. So how we are determining at 1 atmospheric pressure, the normal boiling point, we can project from 1 atma. So 1 atma is equal to 760 mmHg. If you project the same line until it touches this curve, vapor pressure curve, and if you project this to the x-axis, there you can come to know what is the true boiling point or the normal boiling point of your ethyl alcohol. So that is 78.4 degrees centigrades. Then this curve is for diethyl ether. So whose normal boiling point is 34.6. How we can determine this boiling point? At 760 mmHg or 1 atma. So if you project this until it touches this curve, vapor pressure curve, and you project this to the x-axis, there you can determine its normal boiling point is nothing but 34.6 degrees centigrades. So like this, the every component, okay, every component, every liquids will have their vapor pressure curves. Okay, using this vapor pressure curves, at what point, at what pressure, what is its boiling point, we can easily know from that one. So now, for example, if you increase the pressure, so correspondingly its temperature will be increased. So boiling point of water cannot be 100 if you increase the temperature or decrease the temperature. Only this 100 degrees centigrade is valid only at 1 atma or 760 mmHg. So same, the boiling points of various liquids can be illustrated in vapor pressure curves. So the vapor pressure curve is a graph of vapor pressure as a function of temperature. So to find the normal boiling point of the liquid, a horizontal line is drawn from the left at the pressure equal to the standard atmospheric pressure. So this is standard atmospheric pressure. To the left, we will draw the line here. So at whatever the temperature that line intersects the vapor pressure curves of the liquid is the boiling point of that liquid. So this is the boiling point of liquid. Okay, these are called vapor pressure curves, which is nothing but a pressure as a function of temperature curves we will draw. Is that clear?
Yes, sir.
Yeah. So then the most important topic is measurement of humidity. So far we are talking about saturation humidity, then relative humidity. So all these quantities we are talking about. So how to measure that humidity? What is the particular device which is required? What is the particular technique which is required to measure this humidity? So there are three popular methods to measure the humidity. So what are those methods? One is the dew point method. Second one is this one, psychrometric method we will call. Then third one is a direct method. Okay, dew point method, psychrometric method, and direct method. So out of these three methods, first one is a dew point method. So in this dew point method, for example, first what happens? Okay, measurement of humidity. So measurement of humidity. Okay, to measure this humidity, there are three methods. One is a dew point method. Second one is psychrometric method. Or we can call wet bulb thermometry. Wet bulb thermometry. Or we can call sling thermometer. So the device used to measure the wet bulb temperature and dry bulb temperature simultaneously is called sling thermometer. And third one is direct method. Okay, direct method. So in this direct method, there will be an hygrometers. So we have seen in IPC, instrumentation and process control, hair hygrometer, wood hygrometer, wood animal membrane. Then next paper hygrometers or electrical hygrometers will be there. So all this comes under the direct methods for moisture measurement. So out of this one, the first one we are going to see, that is dew point method. So how to measure the moisture from this dew point method, humidity using the dew point method. For example, if there is a vessel or some container, you would say, so there is a gas or a air is there inside that particular. Okay, there is a air is there everywhere. So this air is laden with a what we say, this moisture. Okay, this blue dots will show the moisture which is associated with this particular air. If you want to measure this much quantity of air's moisture content, so what you will do, we have to do is just we will insert some polished, cleaned and polished disc. Cleaned and polished disc we will clean and polished disc. We will just insert into this particular air or moisture laden air, we can say. So this gas moisture we don't know. So gas of unknown moisture, this is unknown humidity. So to know the moisture content which is present in this particular gas or air, or we can say air, so we will insert a disc which is cleaned and smoothly polished. Then what happens? We will decrease the temperature. Temperature of the disc will be decreased gradually using some medium. So we will decrease the temperature. So after decreasing the temperature at some point in time, at some temperature, what happens? Suddenly this moisture, whatever the moisture is there, that will condense onto the smooth disc like this. So the point at which the mist will condenses is called as a dew point temperature. So this is mist condenses on polished surface of disc. The point at which this first drop of mist condenses is called as a dew point. Okay, the point at which first drop of mist condenses is called dew point. And simultaneously, to check whether the dew point temperature, whatever we have evaluated, is correct or not, simultaneously in the next run, what we'll do, increase the temperature gradually. The temperature of the disc will be increased in the next run. So when you are increasing the temperature of your disc, suddenly this mist will disappear. So this mist will be moisture will be once again, the condensed water will be once again transformed to the vapor phase, and it will go and absorb in the air. Okay, the point at which the mist disappears. Okay, this is point at which the mist formation, this one. And in the next run, we will say the point at which mist disappears. At which mist disappears is also called dew point. So finally, so there will be average between the formation. So dew point is nothing but average of temperature between mist formation plus disappearance. So this will be calculated like this. Average of your mist formation and mist disappearance can be averaged, and that will be reported as a mist dew point. So first what we have to do is we have to insert a smooth and cleaned and polished disc inside your vessel, or which is containing whose moisture we want to know, which humidity content we want to know. Then gradually we will try to decrease its temperature. Whenever we are gradually decreasing its temperature, at some point, what happens at some temperature, suddenly a mist will form. That is, the first drop of vapor will be condensed to liquid. The point at which, or the temperature at which the first drop of vapor will condense to liquid is called as a dew point. Okay, to check whether the dew point temperature, whatever we have estimated from the conversion of vapor to liquid, is correct or not, now the same disk will be increased, its temperature will be increased now. So the point at which this all the mist will be disappears, okay, is called as a dew point. So then what we will do, the point of formation of mist and the point of formation of this disappearance of mist, this two will be averaged, and number of readings will be taken and average, and an average temperature which is called dew point temperature will be reported. Okay, so this is the dew point method. Using this method we can easily calculate the dew point temperature. Using the dew point temperature, using humidity chart, yesterday whatever we have discussed, using that humidity chart, if you know these parameters, easily you can calculate what is the humidity which is present in the controlled volume. Is that clear?
Yes, sir.
Okay, same I have given here. Here, see, the humidity of a stream or mass of gas may be found by measuring either the dew point or the wet bulb temperature or direct absorption method. Three methods are there, and the dew point method is if a cooled polished disk is inserted in a gas of unknown humidity and the temperature of the disk gradually lowered, the disk reaches a temperature at which mist condenses on the polished surface. So the temperature at which this mist just forms is the temperature of equilibrium between the vapor in the gas and the liquid phase. So it is therefore the dew point. And a check on the reading is obtained slowly by increasing the disk temperature and noting the temperature at which mist just disappears. Then from the average of temperatures of mist formation and disappearance, the humidity can be read from a humidity chart. So this is the technique which will be used to determine the humidity of unknown gas. Then what is this dew point? So dew point is nothing but it is defined as the temperature to which air and water vapor mixture has to be cooled at constant humidity to make the mixture completely saturated. So to make the completely mixture saturated, we have to decrease the temperature of the particular vapor and gas mixture. So now here if you see on the earth surface, the temperature will be around 87 degree Fahrenheit and its relative humidity is around 48%. When you go further height, okay, from the earth surface, nearly 2000 feet height, what happens? Your temperature will be decreased from 87 to 76. And the relative volatility, the relative humidity is increased from 48% to 69%. When you decrease the temperature, obviously there is an increase in the relative humidity. Means when you decrease the temperature, the humidity content of your vapor gas system will be increased. And further, if you increase the height, if you go far away to nearly 4,000 feet, your temperature will be further decreased from 76 degree Fahrenheit to 65 degree Fahrenheit. As you decrease the temperature, your relative humidity value is increasing. So nearly 100% saturation is happening there. So from this, we can able to know that if you decrease the temperature, your humidity content inside your air will be increased. Therefore, at nearly 400 feet from the surface of the earth, you can find 100% saturated air with a more amount of moisture which is present in the air. So at the dew point, the partial pressure of water vapor equal to the vapor pressure of the liquid. Then the dew point of saturated air equals the air temperature. If your at dew point, what happens? The partial pressure of water vapor which is present in the gas phase is equal to the vapor pressure which is present in the liquid phase. Then the dew point of this whatever the saturated gas 100% saturation will be equal to the air temperature. The temperature at which the first drop of vapor condenses or first drop of vapor appears as a liquid is called a dew point. then the dew point is the temperature, the air must be in order to be saturated. So dew point temperature means lowered temperature at which we have to bring that lower decreased temperature so that the air can be saturated. That is called as a dew point. Okay, is that clear?
Yes, sir.
Okay, so that is a dew point. So for example, let us say one simple case we will take. Everybody will in the winter season, everybody will heat water. Okay, everybody will heat water. For example, this is a vessel. In this vessel, you are having a bucket full of water. So for example, if you are putting this in the stove, gas stove. So slowly you are giving a fire here. Okay, using this fire, what happens? This water content will be boiled. So water content, this will have a vapor pressure. So this water, pure water, will have a vapor pressure. That is, let us say PA dash. So vapor pressure, it will have a vapor pressure. When suddenly this fire is, you are giving a more amount of fire, what happens? Slowly, this vapors, this water liquid will be converted to the vapor. And this blanket full of vapors will be getting in touch, will be go and get in touch with the surrounding air. So blanket full of this water, whatever is there, so that will be, this vapor will be entirely occupying the air. So what happens here? How to measure the pressure of your water which is there in the air? To measure the same one, whenever the liquid water is in the liquid form, so we can measure, we can express our pressure of the water as a vapor pressure. Okay, whenever it is in the gas form, we can express our pressure of the water vapor which is present in the air as a partial pressure. Partial pressure. So let us say this is PA. So the pressure at which the boiling point is nothing but whenever the vapor pressure, so PA dash, vapor pressure of the water, boiling when takes place, whenever the vapor pressure, this vapor pressure of the liquid or water is equal to the atmospheric pressure, then only the boiling will take place. After boiling, what happens? This liquid will be converted to vapors and this vapors will be absorbed on the surrounding air. So how much amount of vapor which has been escaped from the liquid phase to the vapor phase onto the air can be calculated using, can be found out using partial pressure. So until unless it is there in the liquid phase, we will measure the pressure of that particular liquid as a partial vapor pressure. When it is converted to vapor and went to the surrounding liquid phase, then we can express the pressure of that particular vapor as a partial pressure of that particular vapor. So then only this partial, whenever the vapor pressure of the liquid is equal to the atmospheric pressure, then only this particular liquid will be boiling, regardless of it is water or it is ethyl alcohol, methyl alcohol, whatever it may be. Okay, everything will be boiled and will satisfy the necessary condition. This one, partial pressure, vapor pressure of the liquid should be equal to the atmospheric pressure. Then only the boiling will take place. Otherwise, the boiling will not take place. Boiling takes place. Okay, this is a simple concept. What is the relationship between vapor pressure and this partial pressure? So how the partial pressures and this vapor pressures are related? So they are related by the Raoult's law. So Raoult's law, what it is saying, partial pressure for the liquid phase, partial pressure is equal to, so this is first liquid phase, partial pressure is equal to in the gas phase, that is partial pressure means it is in the gas phase, is equal to mole fraction of that component in the liquid phase multiplied by vapor pressure of that component in the liquid phase. That is for the valid for the liquid phase. If you want to calculate the partial pressure for the gas phase, so that is partial pressure of that component A is equal to the vapor mole fraction, okay, mole fraction of that component A in the vapor phase multiplied by total pressure. So then what is the relationship between total pressure and the partial pressures is given by your Dalton's law. So Dalton's law, what Dalton's law is saying? Dalton's law is saying is here the gas phase, in the gas phase component A is there, then simultaneously inert gas is also there, which is not at all solubilized. So that is PB. So partial pressure of component B is equal to mole fraction of that component B into total pressure. So what it is saying is sum of the partial pressure. Dalton's law is saying is total pressure is nothing but how many components are there in that particular stream whose sum of the partial pressures are nothing but your total pressure it is saying. If it is a 3 components, then we can add it as PC. If it is a 4 component, we can add PD. Okay, now here also PC is equal to YC into PT, PD is equal to YD into PT. So this is the concept from where the Raoult's law and Dalton's law has been evolved. Okay, is that clear? So these concepts are very important.
Yes, sir.
Yes, sir. Okay, then next is the wet bulb thermometry, or we can call psychrometric method. Next method we will see. So first method we have covered is a dew point method, and second method is a psychrometry method or wet bulb thermometric method. Okay, second method is psychrometric method of moisture determination, or we can say wet bulb temperature and measurement of humidity. So by measuring the wet bulb temperature, we can easily measure how much amount of humidity which is present there. So how to measure that one? So to measure this humidity, we need to measure a wet bulb temperature. Then we need to measure a dry bulb temperature, so that a temperature temperature depression is nothing but wet bulb depression we will call. So this is WBT, means wet bulb temperature. This DBT means dry bulb temperature, and WBD means wet bulb depression. So the difference between the wet bulb temperature and dry bulb temperature is called wet bulb depression. If you know this wet bulb depression, you can easily calculate the relative humidity using the humidity charts or humidity tables. You can easily calculate. So first let us define what is wet bulb temperature. So wet bulb temperature is nothing but a steady state temperature which is reached by the small amount of liquid which is evaporating into a large amount of unsaturated vapor or unsaturated vapor gas mixture is called as a wet bulb temperature. At the same time, we can also define the wet bulb temperature as the temperature measured by the thermometer bulb or thermometer which is covered with a wick or wet cloth is called as a wet bulb temperature. Then dry bulb temperature is nothing but the temperature of the gas which is measured by the bare thermometer without any covering. Okay, without any covering, if you measure the temperature of that particular gas, so that is called as a dry bulb temperature. So that is called as a true thermodynamic temperature. For example, to measure this wet bulb temperature and dry bulb temperature simultaneously, there is one thermometer is there, that is called sling thermometer, in which two different thermometers will be connected in a single setup. So sling thermometer, we will call that one. So sling thermometer will be looking like this. So first there will be an dry bulb thermometer. So one thermometer which will be called as a, so this will be thermometer bulb. Okay, thermometer bulb. So here the readings will be there to read the bulb. Inside the mercury or something, some element will be there. So this is something like a suspension hole, we can say. So similarly, the same type of thermometer will be there once again. So this is called a wet bulb thermometer. So this bulb is called as a dry bulb thermometer. So this is called as a wet bulb thermometer. Why we are calling this wet bulb thermometer? I will explain you. So this thermometer will have a reading like this. Okay, this one end of this thermometer bulb will be covered using a wet cloth or wet wick, we can say. A wet cloth will be covering this thermometer bulb like this. And one end of this wick will be dipped into a, like this. So other end of the wick will be dipped into the water vessel or water container, something like this. It will be dipped. So wick will be present like this. So wick will be like this. This one end will be covering that particular thermometer bulb, and other end will be dipped inside the particular water container. So as to provide a wetness to the particular cloth. So whenever this is a bare thermometer without any covering, okay, without any covering, this is a bare thermometer. This thermometer will measure a temperature of thermodynamic temperature of the gas. So whenever you allow the gas to flow inside or air to flow inside like this, okay, this will be rotated. This entire thermometer will be, there will be some swinging handle, we can say. Swinging handle. Swing handle, we can say, or swinging handle. Swinging handle will be there, so that we can rotate our thermometer so that air velocity will be greater than 30 meters per second. So at that only some of the effects, effects will be lowered. So this is called as a sighting suspension hole. And this entirely a single panel we can call panel board, onto which there are two different types of thermometers are located. One is a dry bulb thermometer, another is a wet bulb thermometer. To swing this one, there will be a swinging handle. So what happens if there is a flow of air inside that one? First, this thermometer will measure a temperature of the true temperature of this surrounding air without any saturation. Then if there is a unequilibrium, how unequilibrium will develop? Because of unsaturation or undersaturation of the surrounding air. Then what happens? The water, whatever the water is there on the wick, will supply the moisture to the surrounding air. So this slowly, this water drops will be vaporized and solubilized into the surrounding air. And what happens? This entire temperature of the air will be decreased. Then under such condition, what about the whatever the temperature which is indicated by this thermometer, which is called wet bulb thermometer. So to measure this wet bulb thermometer temperature as well as simultaneously dry bulb temperature, there is a one common thermometer which is called as a sling thermometer. So let us assume if the wick is containing one drop, okay, water drop, okay, one water drop, whose pressure is Pw and temperature is Tw. Water drop pressure is Pw and temperature is Tw. And air will cover this liquid film. According to the film theory, okay, within the film only the mass transfer will take place. So liquid film. So first what happens if air is surrounded by surrounding this water drop, so air will have some pressure. Okay, for example, let us say this pressure, air pressure is P. Okay, then P, and for particularly for the air water vapor pressure is A. If A is a water vapor. So this air will have a temperature of T and it will possess some humidity. Okay, so T is the temperature of gas or air. PA is the partial pressure of air. Partial pressure of water vapor in the air. H is the humidity of the air. Then we can define here Pw is the vapor pressure or vapor pressure, we can say, of water. Tw is the temperature of the water drop. Of the water drop. So first what happens? This will be forming a film. Okay, air will be occupying this drop as a film according to the film theory. Then mass transfer will take place within this film. So how the mass transfer will take place first? So first what happens? The surrounding air has to be at higher temperature. So that temperature has to be sent to this water drop. Then this slowly this water drop will be converted to the vapor, and this vapor has to absorb into the surrounding air. That is the process. So mass transfer from where to where it is taking place? Water drop is consuming and the mass transfer is taking place from the water drop to surrounding air. Mass transfer is taking place. So whereas heat transfer, where the heat transfer is taking place, because water drop is at low temperature, Tw is less than T. So what happens? Some part of heat transfer will take place from higher temperature region to lower temperature region. Since T is at higher temperature, So this temperature will be supplied to the water drop and it will vaporize the water drop and solubilize into the air. So heat transfer takes place from reverse direction. That is from the air to water drop, heat transfer will takes place. Heat transfer will takes place. So mass transfer will takes place from water drop to air. Heat transfer will takes place from air to water drop. So this is what going on. First heat transfer will takes place because it is at higher temperature. After attaining this, after transforming the heat to the water drop, this water drop will be getting vaporized and therefore this vaporized water drop will transfer its mass to the surrounding air. It is clear the concept mass transfer, heat transfer simultaneously, how it is going on.
Yes, sir.
Yes, sir. Okay, same thing, the same profile. If you say, if you see, if this is a wick, okay, which is occupied by the water. Okay, wick or wet cloth, we can say, whose temperature is TW, pressure is PW. So same thing, if you see this as a film, air film. So if Z is equal to 0, that is at the wick. Okay, if Z is equal to some delta, so the thickness of this film is delta according to the film theory, that is in accordance with film theory. So now what is happening? Heat flux or heat transfer is taking place from this direction. So heat flux is coming from air film to the surrounding wick and mass flux is going from the surrounding wick to the air film. That is called mass flux. When Z is equal to 0, mass transfer is starting from wick. When Z is equal to 0, heat transfer is ending at wick. When Z is equal to delta, mass transfer is completing at air film. When Z is equal to delta, heat transfer is starting from the film. So this is what going on there. So this air film will be at temperature T and partial pressure of that water vapor is PA. The same representation of this circular film we are expressing as a profile. So same thing if you take this one under normal 2D coordinates. So what happens first? So let us say this is the thickness of the film. So from 0 to delta. Okay, let us say there is a temperature of your water is less. Okay, this is a what we say. Okay, temperature. So this is a temperature axis. This is a pressure axis, let us say. Okay, temperature of your water is less. So TW is less than your T. TW is less than your T. So T will be coming around here. Okay, then what happens? So because the gas temperature is higher, so this is your T. Then when PA, so partial pressure of water vapor is less than, so this one PA is less than your PW. Then only under saturation is there. Because of this unequilibrium condition, the mass transfer is taking place from the water drop to the surrounding. Why? Because from higher temperature to lower temperature, heat transfer will take place. From higher pressure to lower pressure, mass transfer will take place. So PA is less. That's why the mass transfer is taking place in the PW. From PW to PA, it is taking place. The same condition here. So from this one, can say, let us say, so this is some PW, which is at higher pressures, and it will be decreasing from PW to some partial pressure of component A. So this indicates that T will be greater than TW, or we can say TW is less than T. So here PW is greater than PA, or we can say PA is less than PW. Under such condition, mass transfer. So mass transfer will take place from higher pressure region to lower pressure region. So mass transfer is taking place is from water drop to air film. So in the reverse direction, heat transfer is taking place from air film to water drop. This is what the entire concept which is going on. Whenever these two are exchanging simultaneously mass and heat, okay, Here simultaneously when these two are exchanging, air film and the water drop are exchanging mass and heat simultaneously at one single condition at which the steady state temperature which has been attained by this water drop plus this air film is called as a wet bulb temperature. The temperature at which a steady state point is attained, steady state temperature is called as a wet bulb temperature. So under such condition, whatever the temperature we measure, that is called as a wet bulb temperature. So wet bulb temperature is nothing but a steady state temperature or a non-equilibrium temperature which is reached by a small drop or a small mass of liquid exposed under undersaturated condition to the under adiabatic condition. It is led to be saturated. It is led to be occupied by the continuous stream of gas. Then only the steady state temperature which is attained by this continuous gas phase is called as a wet bulb temperature. Okay, is that clear? Wet bulb temperature.
Yes, sir.
Okay, so what is the driving force for heat transfer? The driving force for heat transfer is temperature. Then driving force for the mass transfer is pressure. We know that one. We know that driving force for heat transfer is temperature. Driving force for the mass transfer is pressure. So let us say, so this film, so we'll have a humidity with a mole fraction of that water vapor is Y. Let us say this is mole fraction of water vapor inside the film is Y. Okay, mole fraction of your water vapor inside this water is W, YW, let us say. Okay, mole fraction. So now what happens? We know this formula. So flux is equal to, flux is directly proportional to the driving force or gradient. In heat transfer, flux is directly proportional to which gradient? Temperature gradient. And in the mass transfer, flux is directly proportional to concentration gradient, or we can say pressure gradient. And this proportionality constant will be the mass transfer coefficient in the mass transfer, heat transfer coefficient in the heat transfer. So for example, let us say in the heat transfer, what happens? The flux is denoted by Q. Q is directly proportional to the temperature gradient means T. So temperature, which one is higher? Higher temperature is T is higher, TW is lower. So it cannot be negative. That's why we are writing higher minus lower. Q is directly proportional to T minus TW, in which the proportionality constant is nothing but heat transfer coefficient in the gas. So Hg. So T minus TW. Then in the mass transfer, heat flux, mass flux is denoted by Na. Na is directly proportional to the concentration gradient Ca1 minus Ca2, or we can say Na is directly proportional to the pressure gradient. So here which one is the higher pressure? Which one will come first? So Pw is at higher pressure. So that is Pw minus P. So in which the proportionality constant is heat transfer, mass transfer coefficient. So Kg into some MB we can take, I think, okay, Kg into Pw minus P. If it is a what we say, moles is equal to weight by molecular weight. If it is in molar quantity, then we can convert into the weight quantities easily by just multiplying it with a molecular weight of gas or air. So Pw minus P. So by the relationship, flux is directly proportional to the gradients, we can derive this one. So what happens here at the film? So if this is a drop, if this is a film, so what happens at this particular condition? So at steady state condition, so this mass flux will be equal to the heat transfer flux. Why it will be equal? Because this whatever the evaporation which is taking place, this water drop is evaporating to the surrounding air. Exactly the heat will be balancing. Heat will be temperature will be balancing to the mass of evaporation. Evaporation of that temperature of evaporation. So that's why we can write this as a latent heat of vaporization lambda W. Okay, latent heat of vaporization lambda W H in place of this Hg. that is heat transfer coefficient, we can write latent heat of vaporization into, okay, not this one, okay, here. Okay, in place of this mass flux, we can write in terms of heat quantities, that is lambda W, latent heat of vaporization of water, into this mass transfer coefficient with respect to mole fractions, Ky, into mole fraction of your liquid. Since the driving force is Y, here we have to write YW minus Y. So Y we have to write that one. So what is Kg and Ky? So Kg is nothing but flux mass transfer coefficient. So whose units will be mole per meter square second into driving force. Under G condition, the driving force is pressure. Under Ky condition, it is also a mass transfer coefficient. So the driving force denoted by this one is mole fraction. Mole fraction. So that's why we are writing that one. Na. At steady state, what happens? Mass flux is equal to heat flux under steady state condition. So at steady state conditions, due to this mass flux is equal to this heat flux, so we can say Na is equal to Q. So we know that Na is nothing but lambda W into Ky into YW minus Y is equal to Q is equal to Hg into T minus Tw. Now we can easily tell this one T minus Tw is equal to, so we can easily tell, so lambda W into Ky by Hg into YW minus Y. So this is a dry bulb temperature, T, air temperature. So this is a wet bulb temperature. So the difference between the dry bulb temperature and wet bulb temperature is called your wet bulb depression. Wet bulb depression is equal to dry bulb temperature minus wet bulb temperature is called as a wet bulb depression. So under this condition, what about this equation? This equation we can write as T minus Tw is equal to lambda W into Kw minus Yw minus Y divided by Hg. This we can bring to the extreme denominator, that is Hg by Ky. Hg by Ky. So from the psychrometric chart, usually the ratio of heat transfer coefficient to mass transfer coefficient, that is Hg by Ky, is nothing but ratio of heat transfer coefficient to mass transfer coefficient, is from the humidity chart or the psychrometric data, is popularly reported as 0.227 kilocalories per kg degree centigrade. This is also equal to the humid heat, which is Cs of moist air. That's why we can write this as Hg by Ky is nearly equal to humid heat of the moist air. Then implies we can write this as a Hg by Ky. This we can send to the denominator, that is Cs is nearly equal to 1. So this equation is called as Lewis equation. Lewis equation. Okay, this one. Okay, let us define the parameters, various parameters. We know that T is nothing but temperature of the air. TW is nothing but temperature of water drop, or we can say where WBT, and this is dry bulb temperature DBT. Then lambda W is equal to latent heat of vaporization. Of water, which will be measured in joule per kg in terms of SI units. Then Hg is equal to heat transfer coefficient, which will be measured in watt per meter square Kelvin. And Kg is equal to mass transfer coefficient, which will be measured in moles per meter square second into Pascal, or driving force, or we can say Kg per meter square second into Pascal. Then Ky is also a mass transfer coefficient. Will be measured in same units, moles per meter square second. Now the driving force is mole fraction, or kg per meter square second into driving force is mole fraction. So Y is nothing but your humidity in air, then YW is saturation humidity of air at temperature TW. Saturation humidity of air at temperature TW is called the saturation humidity. So entire quantities, whatever we have defined. So final equation, this is called as a Lewis equation. So this is important derivation, the Lewis equation. I hope it is clear.
Yes, sir.
Okay, for the next class, please revise and come. I will solve once again this one. No problem. Just revise and come once again.